Energy is one of the most fundamental concepts in physics, yet its meaning is more intricate than it seems. From kinetic energy in moving objects to potential energy stored in stretched springs, energy takes on many forms, constantly transforming but never disappearing. Its history stretches back to debates between great minds like Newton and Leibniz, with contributions from pioneers such as Émilie du Châtelet and Emmy Noether. In this video, we explore the nature of energy, its connection to mass and its role in the expanding universe, where even the laws of conservation may not fully apply. Join us for a fascinating journey through one of the deepest topics in physics, revealing just how integral energy is to everything we know. What is energy? Energy is a fundamental concept. Energy is a cornerstone of both classical and modern physics, though it can be hard to define precisely. General definition, often described as the capacity to do work, though the technical term work can be difficult to grasp. Kinetic and potential energy. Kinetic energy. The energy associated with motion, whether it's linear movement, rotation or vibration, potential energy, stored energy created when an object is moved against a force, such as lifting an object or stretching a spring. The history of energy concepts. Newton versus Leibniz. Newton emphasized momentum, which depends on the mass and speed of an object. Leibniz focused on energy, relating it to both the object's mass and the square of its speed. Émilie du Châtelet demonstrated through experiments that an object's impact in clay depended on the square of its speed, advancing the concept of energy. She proposed that energy is conserved and derived the formula for gravitational potential energy. Conservation of energy and Emmy Noether's theorem. Noether's theorem states that conservation laws result from symmetries in the natural laws. If the laws of nature remain constant over time, energy is conserved. If these laws are consistent across different locations, momentum is also conserved. Energy beyond moving objects. Massless objects carry energy. Photons, waves in electromagnetic fields, carry energy despite having no mass. Mass-energy interchangeability. Einstein's theory shows that mass and energy can transform into each other. Protons and neutrons get their mass from the interactions and motion of nearly massless particles inside them, resembling tiny tornadoes of energy. Energy and the expanding universe. Energy conservation is not absolute. In an expanding universe, energy conservation is more complex. Dark energy. As the universe expands, the total energy from dark energy increases with volume. Redshift light from distant galaxies loses energy as it shifts to redder wavelengths. Impact of general relativity. Noether's theorem assumes static space and time, but in an evolving universe, conservation laws become more complicated. Energy as a continuous exchange. Interaction between fields and objects. Potential energy arises from the interaction of forces like gravity or electromagnetism with objects. Kinetic energy reflects the motion of these objects and fields, transforming back and forth between kinetic and potential forms. Energy's dynamic balance. Energy flows between different forms but remains constant, except when considering the universe as a whole, where conservation is more nuanced. Conclusion. The beauty and complexity of energy. Two views on energy. Energy can appear deeply complex or beautifully simple depending on perspective. Energy's role in modern physics. Energy remains a key concept in physics, continuously revealing new insights.